Hey everyone, let's dive right into this explainer. We spend a ton of time learning how math works perfectly, but today we're flipping the script. What happens when the gears completely grind to a halt? When does a perfectly good-looking graph fail to be a mathematical function? It's absolutely crucial for calculus and algebra, and honestly, understanding how something breaks is the best way to understand how it works.
Here's our roadmap for today. We'll start with the broken machine, check out the vertical line test, get our math dose with domain, tackle the fraction challenge, and wrap it all up with the final test. Section 1. The broken machine. Remember how we always say a math function is like a highly predictable factory machine? The absolute golden rule of this machine is predictability. You put in a specific raw material, your input, and it must give you exactly one specific product. But imagine dropping in one piece of metal and it randomly spits out either a bicycle or a toaster. Total chaos, right? Well, that's exactly what happens when a math machine breaks. A functional machine has to have a strict rule where one specific input yields exactly one specific output. It's just like the pre-programmed keys on your calculator. When you press the square root of 9, it gives you 3. It doesn't give you 3 on Tuesdays and 5 on Thursdays. It gives exactly one output. That uncompromising rule is the literal heartbeat of a working function. Check out the visual contrast here. On the left, we've got our working machine, the classic parabola, y equals x squared, opening upward. Every single x you put in gives you one specific y. But look at the one on the right, x equals y squared minus 2, opening to the right. If we input the number 2 for x, the machine suddenly spits out two completely different y values at the exact same time, a positive and a negative. Because it gives two outputs for a single input, it is definitively not a function. Section 2. The vertical line test. Now, there is a really elegant visual shortcut to spot these broken machines without needing to do any heavy algebra. It's called the vertical line test. The rule is simple. If you drop a straight vertical line anywhere through a graph and it hits the curve more than once, that machine is officially broken. It fails because that vertical line represents a single input, and every time it crosses the curve, it's hitting a different output. So if we run that test on our right opening parabola at the number 2 on the x-axis, that vertical line cuts directly through two distinct points. One is above the axis, one is below. This simple visual trick perfectly proves that the input of 2 has two different outputs, and just like that, it mathematically fails to be a function. Section 3. Domain, the math dose. Let's open up the machine and look at the algebraic gears inside. To do this, we need to talk about domain. You can think of the domain as the exclusive VIP list of numbers that are actually allowed to enter the machine without causing an error. It's the complete set of valid inputs. If a number isn't on that VIP list, the machine's doors simply stay shut. Here is how we calculate that list algebraically. Let's take the radical function f of x equals the square root of x plus 2. The ironclad rule here? Absolutely no negative numbers under a square root. To find our safe numbers, we literally just set up an inequality based on that exact rule. X plus 2 must be greater than or equal to 0. Solve that, and we get x is greater than or equal to negative 2. Boom, that's our domain. Our safe numbers start at negative 2 and go up from there. Let's test it out. Input a 2, you get the square root of 4, which is 2. Perfect. Input a 7, you get the square root of 9, which is 3. Works great. But what if you try sneaking a number smaller than negative 2 past the bouncers? Let's say negative 3. Negative 3 plus 2 is negative 1. You are basically asking the machine for the square root of negative 1. The machine will instantly halt, crash, and throw an error. Negative 3 is simply not in the domain. Section 4. The fraction challenge. Let's introduce a new enemy to the function machine, rational functions, or basically fractions. Let's look at g of x equals 1 over x squared minus x. With fractions, the unbreakable mathematical rule of the universe is that you can never, ever divide by 0. So to find our domain, we have to actively hunt down the inputs that destroy the denominator. Set the denominator to 0, x squared minus x equals 0. Factor it out to x times the quantity x minus 1 equals 0. And just like that, we've exposed our enemies, x equals 0 and x equals 1. By factoring that denominator, you are thinking exactly like a true mathematician, explicitly separating the safe inputs from the forbidden ones. Our domain here is all real numbers except 0 and 1. If either a 0 or a 1 tries to enter this machine, they are immediately rejected to prevent a total mathematical catastrophe. Section 5. The final test. To wrap up this explainer, I'm handing the inspector badge over to you. Take a look at this S-shaped curve resting sideways on the graph. Based on everything we just covered, is this a function? And can you deduce its domain just by looking at it visually? Drop your detailed analysis in the comments below, and the very first correct answer gets pinned. I'll see you in the next explainer, where we dive into the essential types of mathematical models.